really a trip. And that's how this recording will start, with me saying that it's a trip.
Is that tie-dye shirt handmade?
It is, but not by me. I get them from, I have that other tie-dye, I don't know if you noticed, it's got like the little spiral kind of thing on it too.
That one's pretty cool.
Yeah, I get these from Bobby's Hippie Shop on Etsy.
Oh.
Yeah, she
Wow.
does a good job. She does a real good job.
It looks like
Thanks.
You look just like the Toad or something.
I look like what?
Like if you like, I don't know. It looks really trippy.
Yeah, it's like a sky. I was thinking this is
Yeah.
kind of like the sky a little bit.
Have you seen that guy on TikTok that makes like crazy complicated ones?
Yes.
It's crazy.
Oh man,
Insane.
utterly insane. Yeah, I think I know the guy you're talking about. Like patterns you wouldn't think you could do by twisting. And,
I want a tie-dye shirt.
Utterly insane. Yeah, Bobby's Hippie Shop, Etsy. Great lady. Got lots of people's shirts from there. Alrighty, so we're on to the next stage of our class. Started off with logic, moving into the study of, let me kind of show you what's coming up for this next unit, really. So we're going to talk about sets, collections of things. Sounds like could be very vague, and in some ways it is, and we're going to talk about the vagarities of that. Is that even a word? I don't know. But the vagueness of that all, and how do we make it precise? And you're going to see huge connections between this and the logic that we just did, and you're going to see them today. They are intimately intertwined. And then we're going to talk about something that I can't wait to talk about, because nobody understands these anymore. Functions. Like literally, like even people in my 400 level math classes, like I've got these math majors who have been around doing math for 3 years, and they still don't quite understand these. And actually, this is what causes people the most trouble in math. When people are having trouble in math, it's usually because they don't quite understand what a function is. You're going to understand what a function is. You're going to be like super powerful mathematically. So this is just like maybe the next couple of weeks, for sure. Let's start off with talking about sets. There's a new assignment up. I've learned some things about making assignments, right? So hopefully that prep for today, did that take too long?
No.
Awesome, that was my intent. I was thinking like 7 minutes, 10 minutes.
10 minutes, that's fine.
Yeah? Beautiful. Yeah.
It didn't take me 7, but it was easy.
Okay, cool, okay, awesome. Easy is all I was going for, because you just had an exam. I didn't want to like brutalize you, because you didn't have long to do it either. There'll be one for Monday, but I don't know what it is yet, because I want to see where we get to. So there's a new Connect homework. We might even start on it today in class. It's due next Tuesday. So what would be great is if we could start on it before Monday and have questions, and you know I'll talk about it as much as we need. I hope you know that about me. Now, I hope you've learned a few things about how I run my show. So, due next Tuesday, and that's it. This should actually be like kind of nice and chill. I think this won't be bad. I think the prep for today might have been harder than this assignment, because that prep had like a bunch of empty set stuff in it, right? Or not? Was I,
Yeah.
Like I think that stuff's weird. I think that stuff's like baffling in a way. We'll talk about it. Let's just start talking about sets. It's really one of my favorite things to talk about, because we'll get down into the history of math, and we'll talk about a time when math actually fell completely to the ground in flames. In the early 20th century, in the 1910-20 era, people weren't sure math was actually legit or not at the most basic level. You don't hear this story at all. Like very few people know this story, but you're going to know this story. You're going to know why it all came about. So let's start off a little bit with just a definition. A set is and this is kind of what got everybody into trouble, this definition. A set is a collection of objects, and they are called elements of the set. That's the definition there, and the elements are the things inside the set. So
how do you even talk about this? How do we write about it? How do we think about it? One of the best ways to think about it is with a picture, but that can be super misleading, but we're gonna be okay. So this little boundary here represents a collection. So the collection is inside here, or a collection of things. And the things inside here, let's say there's like something that maybe is an alligator, and something that's a bat, and something that's not in that collection, and it's a cat maybe. These don't have to be any of these things, but they could be. This could also be an almond. This could be butter, and this could be chocolate. But it could also be a number, and a different number. So the collections we're talking about can be anything you can imagine can be a set. Any collection of things. The people in this room, we're a set. Just everyone in the room, all of us. How many of them? 1, 2, 3, 10, all 10 of us. That's a set. The people in this room who, I gotta watch. I always come up with the weirdest fucking things to like say, and then I have to filter myself, just so that I'm like, just being a decent member of society. The people in this room wearing sandals. That's a set. Who's wearing sandals? These count. I got my Bergs. Anybody else wearing?
No, I have a question.
Oh yeah.
So,
But hold on. Is anybody else wearing sandals? I was gonna see. Okay.
Oh man.
So the set of people in this room
Next
wearing
time.
sandals, just numero T here. Yes.
so a set is just a group of objects with at least one similar property. Do they have to have a similar
Ooh.
property?
Yeah, well, no,
No.
not necessarily. What a great question. Sometimes they will and sometimes they won't.
Okay.
So, for example, I could say the set of all things in this world. And I guess in some ways,
It's a thing.
it's a thing, and they do share the fact that they're in this world. So maybe that would be an okay thing to add. I didn't want to. Did everybody hear Cadence's question? Yeah, it's a great question. I don't think you could go wrong by saying that either.
Okay.
Yeah, even if that property is nebulous as hell.
No, absolutely.
Yeah, okay, I love that. Yeah, absolutely, you could say that. Let's actually add that to our definition. Set is a collection of objects sharing a common property.
Yeah.
Yeah. Ooh, I love that actually. Yeah, absolutely. That's a philosopher. Perfect. A logician. Logician. So, these things here are in the set. This picture is meant to imply the idea that, or convey the idea that A and B are things in the set, but C is not. So here's a little notation. I could call this set S, and I'm just gonna name it. So S is a label for the set. So when I say set S, I'm referring to these things here sharing whatever common property that I have. A is in the set, B is in the set, so here's how I write that. I say A, and I use this little pitchfork symbol, and it really stands for element of. Element of, or you could think is an element of. It really stands for that phrase, S. This just means A is in S. It's in that collection. B is in S. And I'm trying to make my S kind of, see, I've got these little fancy serifs on there, or whatever those things are called, those fancy little ends on the S. But C is not. So the way I would write that is I would say C, and I use the element sign and slash through it to say that C is not in S. So C is not in S. Just a little bit of notation there. We're pretty much going to use capital letters to signify sets. So convention is this, and this is all over mathematics. Use a capital letter to indicate a set. All right, so let's talk about, what I love about what you said, Cadence, is the similar property is, it's kind of hard to describe a collection without having some kind of way to understand what's in it. So here's the various ways we can describe a set. The first one is the most straightforward, and it's called the roster method. So first is roster method. And that's literally, a roster is just a list of things. What are you guys up to back there?
Nothing. Math's cool. Math's awesome. I love math.
Right, don't get on probation.
No, Dr. T, you're the best math teacher I've ever had. That's why I'm taking your class again.
Well, thanks, Joe.
Yeah, I've had some really bad math teachers, so you're the best one.
Well,
Hands
thank
down.
you.
Like, hands down. Like,
Thanks.
you're gonna get a good gift when I graduate.
Are you the guy who
If-
crashed the Beamer into the gate? Cool, you don't have to get me any
What
gifts.
ransomware attack?
That was a lovely, that's gift enough, thank
Yeah.
you.
Still get
I don't know what was going on before that, but
Oh, the roster?
you pulled the roster. No, I know what was going on here. I don't know what was going on back there. So the roster method, this is just basically a list. So for example, I could have a set A. See, I'm gonna have to get some kind of little mirror shit. Don't make me feel like I need that, Joe. So this set here, I could just have some numbers in it. 3, 2, -7. There's a nice set. That set S over there, I could denote it like this. Notice these braces. So I'm making them a little sloppy. That's the actual symbol. It's like an S reflected upon a pond. Like that, yeah, it's like reflecting in the, yeah, exactly. So that set S over there was just A and B. Those are the things in it. We have some fancier sets. Let's talk about some sets that, as a computer scientist, and especially in the class, they're going to become important to you. So let me do this so Sophia can see everything. So here's some important sets that we'll come back to over and over again. The first one is denoted with this fancy Z. And we've used that, right? What does that one stand for?
The domain of all integers.
Yeah, exactly. It's all integers. It comes from the German word Zahlen, and it just means integers. So this set, now check this out. I can't list all of them. I can't list them, there's infinitely many. But I can give the reader a sense of what's in this set. Notice how I've got these ellipses indicating and so on. And hopefully I've got enough here to indicate the pattern to whoever's looking at this. And they can look at that and go, oh, totally. I know that this is in that set. 17 is in there, even though it's not listed. I also know that pi is not an element of that set, because pi is not a whole thing. Pi is an irrational number. And it's got infinitely many decimal points. Decimal numbers. It's got an infinite decimal expansion. So that's a really important one. We also have the natural numbers, which actually probably came first. Let's talk really quick about the history of numbers, since we're here. A brief history of numbers, doesn't start there. So first off, that's a W, a fancy W of some kind. It stands for the whole numbers. 1, 2, 3, 4, up. Those are the whole numbers.
So not negatives.
Correct, sir, yeah. These are kind of the first numbers. These are the primal numbers that when people were just worrying about how many sheep do I have, how many arrows do I have in my quill, you know, just like the living numbers, the numbers that just help you keep track of life. They're the whole numbers. And then along came this number. and it was added into the collection. And every time a new number is added, these are the natural numbers. Every time a new number has been added historically, somebody's died because of that number. Somebody got killed because they dared to suggest that there was something that we didn't know about that was beyond our comprehension. The very first zero, I think happened maybe a couple thousand years BC, and it was found on a Hindu temple.
That was the Mayans.
Was it Mayan?
It was either the Mayans knew it before Europe. or
That's
the
for
Indians
sure. The
knew it
Mayans
before-
definitely. I think the oldest zero was on a Hindu temple, but
Okay.
the Mayans definitely knew about it as well.
Okay.
Yeah, you're right. Yeah, because they had that really weird number system.
Mm-hmm.
You've studied this apparently.
Very briefly in like 5th grade.
That's awesome. That's awesome. So they had that really weird number system, and I think their zero was like something like this, and it was like an empty basket. Does that ring any bells of any
A
kind?
little bit, yeah.
Yeah, yeah. So they had a really cool number system. They also used base 60, I think, which is crazy. Yeah, base 60. Yeah, I'll bring in some stuff about that. But yeah, that's amazing. 10 makes sense because I'm looking at 10 fingers right here, right? And I can count on them. But 60 is like, wow, mind-blowing. But I think that the reason they use 60 is because they did a lot of trade. And 60 is divisible by so many different things. And so you can cut 60 into halves, into thirds, right? 60 is divisible by 2, divisible by 3, 4, 5, 6, 10, 12, a bunch of numbers. So it really worked good to keep books that way, just for easy divisibility. So, but the addition of the zero, that was a big deal. To accept that 0 is a number, not just like keeping track of things like, oh, I have no arrows in my quiver, but just for bookkeeping on its own, and then the whole idea of numbers just for their own sake didn't come till much, much later. And then someone had the audacity to suggest negative numbers. I don't quite remember when that happened. Do you, Sophia? You seem to have a good sense of number history. That's awesome. Yeah. Yeah. So then, when we add in the negatives, we get the integers, right? So we've got Z. The idea of a negative quantity was undoubtedly, I'm positive, considered heretical at some point. God wouldn't make a deficit, And most of this stuff always comes from somebody in religion. Religion causes so many problems in the world, and it just like locks people's minds into certain modes, and they can't break out of them. And then suddenly you're on fire on a stake because you wrote a -2. Yeah, for real. Yes.
Banish him.
Yeah, exactly. How dare thee? Thou hast befouled the name. Okay, so then there came the idea of fractional things, and the Greeks were really into this. So we have this whole number system called the rational numbers, and it's denoted by a Q. That's a pretty good Q, I have to say. So this is the rational numbers. We will use this for sure. And it is equal to the set of all fractions. And this is pretty much where the Greeks got stuck. They wanted to they believed that everything should be commensurate. And in other words, two things can always be in a perfect ratio to each other. And, well, that's not quite the case, because then came along Pythagoras. And Pythagoras was messing around with triangles, as you may or may not know, Pythagorean theorem, right? We know that this side squared plus this side squared is this side squared. And then Pythagoras said, well, wait, what if I have a triangle that is 1, 1, and then what's this side? Well, it was the square root of 2, which cannot be written as a fraction. And we could prove that using a method of proof we haven't quite talked about yet. But this number here can't be written in the form of a whole thing over a whole thing. This is called irrational. So we, at some point, Pythagoras didn't get killed for that. Pythagoras had all sorts of weird stuff going on. Oh yeah, yeah. The Pythagorean cult was
Oh gosh.
really, so what do you know about him? That's cool.
I mean, I remember learning about it. I can't remember specifics right now, but like, they were really weird.
Mhm. I know that castration was a requirement to be in the cult. I'm out, you know, right there. But like, and I think a lot of people, like any cult where that is like part of it, it's no thanks. No thanks. So,
Carry on there.
sorry, I apologize for
They don't want to carry on their math.
the imagery and all of that.
Genius.
So
Yeah.
this number set I is the collection of all numbers that can't be written as a fraction. And it turns out this is most of the numbers. Most numbers fall into this category. So the Greeks were only working with a very small set of reality, or models of reality, as A over B. So I want you to notice I'm writing out sets and descriptions here. These are descriptions of sets. They're pretty loose. This one is getting a little bit more precise, so I'm adding a little more precision as we go along. Let me show you a more precise way to write this Q. So this is semi-precise. But for more precision, I would write these definitions like this. And this is what we're going to practice with. This is part of your Connect homework. The set Q is the set of all things that look like this. And what I'm using here is called set builder notation. So this is the collection. As soon as I see this, I read this as the collection of, or the set of. That's how I read that first brace. And then I see 8 things of the form A over B. So let's put that. Things of the form little stool here, A over B, and then I put this colon, and I read this colon as where or such that, and you'll probably hear me say such that a lot, such that A and B are elements of the integers. So I'm saying that A and B are whole quantities. What should I also make sure that I don't divide by? What's a bad thing to divide by?
0.
0, yep. So we make sure that B is not equal to 0. So this, being able to look at that and understand what it is relaying to you is part of what we're talking about today. How many folks have seen this notation at some point in their lives? This kind of, nobody? No? Cool. Really? I feel like somewhere you must have seen something like this, but hey, whatever. You're in a class, you're hopefully not seeing stuff you know left and right, so that is fan-freaking-tastic. Let's talk about some other sets. Now, this set here, this is R, and this is the real numbers, the set of real numbers. And this set is a combination of all the fractions, everything that can be written as a fraction, and everything that can't be written as a fraction. So this is the rationals and the irrationals together. And the way to think of this is really, it's just all numbers that you'll ever probably deal with. We can lift off from there. So like right now, remember how this, let's look at the little story. So we started with W, the wholes, and then we booted up to the naturals by adding 0, and then we added in the negatives, and we got Z. And now and then we added in the fractions, and we've got Q. getting more and more numbers all the time, and now we've got the real numbers. Take these and toss in all the things that can't be written as fractions. So, like, what's in here? You know, so the square root of 2, that's an irrational. Pi, what's this number? Joey better know this number. But who else? I can think of a couple people who might know this number. Daniela certainly knows this number. I just don't know who's all had calculus in here. What is this number? Danielle, what's that number? Just say what it is. Just read it.
E.
Yes, that's it. Yeah, beautiful. It's E. It's E. That's it. That's beautiful, beautiful. But this number is actually really important in the world. It goes on and on forever. This number is absolutely essential to do calculus or to study exponential growth and decay. So in studying radioactivity, in studying the growth of cells, when they're growing exponentially, this number is absolutely key to all that. I don't think we'll mess with it this semester because it's not part of discrete math. All this stuff is part of, if we were thinking about the reals, that's all continuous math. Because the real numbers can be represented. What were you going to say?
They don't go on. Well, like the numbers go on, but they themselves don't go on forever.
Yes, so there's definitely, are you thinking about this case,
Yeah.
the fact that those go on? Yes, so definitely there's that like infinite part there, but the continuous part comes from the fact that if I look at the real numbers, this is the real line. Have we all seen this? Seen the real line, the real number line? I can move continuously across here and always be in contact with some number. Whereas if I were to just do the integers, they would be dots like this from that line. And so that's discrete. They're separate. There's still infinitely many of them, but there's a different nature to their relationship. Cool. All right, let's see what else I got on my sheet here. What does this set look like? So I'm going to ask you, can you give me, I'm using set builder notation, can you give me a roster of these numbers? So given, good Lord, that word is given. Given each set, write the roster form. So this first one that we've got here is a set O, and it is equal to the collection of all X and Z. So now I'm switching up the notation left and right. There's no standard way, so you have to read this and get used to like picking it apart. It's the set of all integers. That's how you read this. Such that, and then I'm going to give you some conditions. So X is even, and X is greater than 10. What does that look like as a list? So just take a second, don't say it out loud, but try to write it for yourself. I'm gonna kill myself on that chair if it doesn't end. What is this, Nick? Not Nick, shoot, that's
Oh, no.
No. Why am I not, why am I calling you Nick? Alex, sorry.
Yeah, you got it.
Yeah, apologies. Alex, what is this, sir?
Like, what do you mean exactly?
So, tell me a number that's in here.
2.
Is 2 greater than 10?
Oh,
So check it out, yeah.
that's-
Let's have this conversation, I love it.
12.
Beautiful, because 12 is even and it's bigger than 10. Is there anything smaller in that set? No, you're absolutely right. So you just started from the left and you're working on up. And then what's like the next one in here? Somebody else tell me.
14.
14.
16.
Yeah, beautiful.
18.
Nope, okay. Yeah. Yep, and then at that point, the reader has the rhythm and they can play the song. right, so I'm good with that. Let me give you another one. What about this one? Let's call this the set T. I like making these fancy caps. So it's the set of all x and z, it's the set of all integers such that x is less than 3 and x is greater than 5. What's in this set?
Nothing.
Ooh, who said that? Who said nothing? Came from somewhere. Is that you, Yvonne?
Yeah.
Yeah. So why is that?
Because there's no integer that's less than 3 but greater than 5.
Right, it's contradictory. You can't be less than 3 and also greater than 5. So this set is empty. There's nothing in here. So there's nothing in this set. And let me introduce a piece of notation. So we say T is equal to the empty set. This means an empty collection. There's nothing in it. So this is the empty set. And you probably saw that in the prep for today, yeah? And then they started doing weird stuff like the set of the empty set and all sorts of crazy
so many
shit.
brackets.
So many brackets. And we had like, that was just like a warm-up, a weird warm-up. But we're not gonna mess with that. That was the only time you'll have to do that crap. But wanted to get you looking up stuff and having to think about sets. Let's go back to R, the real numbers, because we've got some special notation because of that number line. And if you've ever taken any other math class, you probably have seen what we're about to use. So this is called interval notation. And interval notation is a way to describe stretches of the real line. In other words, i.e., collections of real numbers. So, for example, if I say, here's the real line, going on forever and ever, and here's 0, and then here's 1, 2, 3. You gotta have some anchors so I know what's going on. If I want to talk about the set that's everything not including 1 to the right of 1 and including 3. So check this set out. This set is the set of all reals that we have x is bigger than 1 and less than or equal to 3. Notice how I've got an open circle to not include the 1, closed circle to include the 3. So I can use this interval notation that uses parentheses and brackets. Does that look familiar? Yeah, cool. So a lot of times people think of this as just 1 and 3. This is all the numbers between 1 and 3. So it's this picture, it's this set, and it's this. So we have 3 ways to describe this real number set. What do you think this one looks like? And I'm going to get a little more general now. What does that represent? Kind of, variable here, literally. What does the picture look like? Here's A, here's B. Could someone tell us, just like how to draw it?
It's 2 solid dots.
Beautiful, Abraham. So it's 2 solid dots, and then everything in between. Yeah? Lovely. Nicely done. Cool. So this parenthesis means don't include. The bracket means include that point. And so then we have, let's just go ahead and write a couple more out here. Just so we have this one here, that's this, A, B, we've got A all the way up, don't include B, got an open, and then this one where it's open on both ends. Sound pretty reasonable? We're gonna be messing around with these things. To and fro occasionally. How many people in here have coded this month, have written code?
This month.
This month, yeah, everybody, awesome, yes. What language have we used? What?
Java.
Java.
HTML, JavaScript, and CSS.
Nice.
I haven't coded this month yet.
You haven't coded this, when's the
No.
last time you coded?
Last year.
And what'd you code in?
Java.
Java?
HTML and CSS.
HTML?
And
No.
JavaScript.
And, PostScript?
JavaScript.
JavaScript, okay, cool, oh, you say that, cool, okay, awesome.
Java.
Java?
Java.
Java? Java? Yeah, nobody's used Python?
They don't teach us that here. It's lame.
It's
They
crazy.
do. No, they don't.
You've
They-
used Python.
I taught
That's
freaking.
Beautiful,
I taught to
beautiful. Was it like a physics
guy.
class?
No,
It was great. Yeah,
Oh, CS, okay, good, good.
And
I'm
this was
glad.
my class, and I flipped like.
Python is a good language.
What are you on?
Lots of fun.
Database application.
Anybody ever coded in assembly language?
No. So I need to take that.
I mean, it was a model assembly language, but still.
Yeah, yeah, that's good. So like at the level of the machine, like going down and opening registers and messing with that, it's pretty intense.
Yeah.
Back in the day, that was how you wrote fast code. If you wanted to write a video game, you wrote it in assembler. You ever heard of the game Roller Coaster Tycoon?
Yes.
Yeah, that was one of the first really popular games. It was, first off, it was huge. It was a huge game. And it was written entirely in assembly language. That guy went in and took, all by himself, it was written by one person in assembly language. And I encourage you as computer scientists to see what that would entail. Because to just like a for loop, you can't, huge, everything's huge, and Kyle knows what I'm talking about. Can you imagine writing a video game in assembly?
Yeah, I imagine that guy just hates himself.
Well, he hated himself all the way to the bank.
Apparently,
That's for sure. So, in Java, you use sets all the time. You want to declare a variable, you have to describe where that variable's coming from. And I haven't done Java in ages, but would you write something like this? Would you write like int x? Yeah, so check it out. So you like declare this at the beginning of your code or whatever module you're writing on, or class, things like that. And do they use semicolons in Java as well, or do we not need those?
Yes.
Yeah. So you write this. What you are saying is that x is an element of the integers. So in code, you're doing this stuff all the time. This isn't just abstract math. This means this, and vice versa. What if I write this? Is float, that's a Java term, right?
Yeah.
use double though.
Use double, oh, so you would say, yeah. So this would be like single precision. If I wanted a double precision, I'll do this, yeah? And so that's a double precision real number. It's not even all the real numbers. It's just the ones that can be written with this finite precision. What is that, like 64 bits or something like that? Yeah. That doesn't get you many numbers. It just gets you a good enough numbers. So just realize the set stuff is not just out there. It's not just the weird stories I'm about to tell you. Let's do an example first. Talk about how to compare some sets together. So let's talk about comparing sets. And the ways to notate that and to do it. So I'm going to put a bunch of sets up here. So here's A, it's 2, 4, 6, 7. B is 2, 6, 7, 9. Yeah, all right, doesn't matter what order I write it in, that's okay. Maybe it's cool to not do it in that order. C is 2, 6, 7. Now I went to great pains to make up these dumb examples. 9, and then E. Got 2 more, I got 4 more to write. So E is 2, 6, 7. Wait, I already did that. Yeah, that's okay. It's totally. Okay, yeah, I'm trying to make it like one of your problems you have to do. So it's okay that some of these are the same set, just so that you know what to do when you get there. 27. Okay, cool. So here's a bunch of sets. Are any of them essentially the same? So it doesn't matter what order I write things in. One thing to keep in mind is order is unimportant in a set. Did I write 2G? Sorry, thanks. Yeah. So the 2Gs, so these two sets are the same. So we would literally use equality for that. I would say G equals H because they have exactly the same number of elements and the same elements included. They're identical sets in every respect. Even if I had written this like this, which I probably should have, still the same set. Order is unimportant. Let's take a look at A and B. How do A and B relate? Is there any relation? Well, actually, let's start off a little smaller. How about C and D? Is there any relationship between, yeah, okay.
C would be a subset of D.
Oh, so you got the lingo already, yeah? So this is a part of D. So what we would say here is C is a subset of D. So this notation here looks like I'm writing less than or equal to. I gotta get a little softer on that. And in some ways, it's kind of like less than or equal to,
Yeah.
right? It's like this thing they're relatable, and this one has less in it.
That's a good way to remember which one goes which way.
Absolutely, yeah. So this is, let me write this out, C is a subset of D. Because, let's link this up to stuff we've already said, because if X is in C, then, check it out, I'm using logic, X is in D. So this is an if then, yeah, Joe.
So C is also a subset of B then?
Say that again, sir.
C is also a subset of B then? right?
Absolutely. Yep, nice. So C is a subset of B. Absolutely. What about F and E? What would I write here?
F is a subset of E.
F is a subset of E. So I would, exactly, so it's pretty obvious that F is inside there, right? But we can write this in a slightly different way. And I wanted to show that you could also use this as superset. So I could say here, E is a superset of F. That was why I wrote them in slightly different order. And again, in cadence, it's like you can see the less than or equal to pointing toward the smaller one. Yes?
Okay, so would B and D are equal, but then would also it be like a non-proper subset since all the values are the same, like the one without the line underneath it?
Yes.
Okay.
Yeah, absolutely. So, yes. So let's talk about what Cadence just brought up. You can use this equal line if you have this allows for the possibility that they are actually equal. If I wrote, and let's just do this here, F is a proper subset of E, that just means I clearly know they're not equal. So this is like strictly less than. It's just like less than. There's no possibility of equality.
That makes perfect sense.
Awesome, beautiful. So this is, let me use this, what Cadence brought up here and write it up here. This is a proper subset. And that just means no way equal.
Wait, why would it be that though? Like, couldn't you just, like, because theoretically, if you added another term to F and it was a 7, wouldn't it be equal? So wouldn't it have the potential to be equal?
Yeah, I mean, sometimes, like in general, Joey, absolutely. Like this is totally okay.
Okay.
It's allowing for the possibility of equality, but maybe you want to communicate with a little bit more precision and just say, this set is definitely not equal to this one, but it is part of it.
Okay, so when do you really want to use the different ones, like the proper subset? And
Probably doing like math that we'll never do in here.
Okay.
So it's like getting to things at that subtle level, we don't even have to worry about. Just know this, you can't go wrong with that.
Alright, I like that.
That's like no. So what about, now let's go back, what about A and B? Is one a subset of the other, or vice versa? Yeah, do we see? Like, boy, if I didn't have that 4 in there, A would be a subset of B. And if I didn't have this 9 in here, B would be a subset of A. But right now, neither is the subset of the other. They're incomparable. So these two sets, A and B, are incomparable. So I couldn't make any statements at all like that. They do have some relations. They share some common things, and we'll talk about that in just a second. Probably in a minute, because I want to talk about something cool first.
Is there notation for A and B are incomparable? Is it just the subset of the length, or is that not a thing?
Yeah,
Equal with the line.
we'd have to use like more than one statement to communicate that.
Okay.
Yeah.
Okay.
I would, yeah, and I don't want to get to the language yet because I'll get there, but yeah, there's no like nice, there's no, well, you know, maybe that, I've never seen that in set theory, but it gets the point across. Yeah, yeah. I want to talk about this loose definition of set that we're using. Let's keep these guys up here for a second. So what we're going to do in this class is what's called naive set theory. And this was essentially established by a mathematician, logician of the name Georg Cantor back in the early 1900s. Cantor went insane.
They all do.
And he was probably insane the whole way through to do the things he did, because Cantor brought us all our modern understanding of infinity. And there's more than one infinity. There's different infinities and they're not the same. And we're not going to get into that here, but I love talking about that. But Cantor showed us how to build new infinities. Like, what kind of mind do you have when you can do that, right? That's like amazing. But he brought us this basic idea of set theory. And then he wrote this set. C is the set of all sets that are not contained in themselves. And let me write that out in fancier notation. So just read that and just try to process that for a second. That are not subsets of them. Yeah. So it's the set of all set X. X is a set such that X is not an element of itself. Like, you don't have to worry if this hurts your brain, because it hurts everyone's brain. And Cantor wrote this, and this is what broke math. Because he wrote this thing, and let's talk about what the trouble is here. So you ask yourself, wait a minute, so is C inside of itself? Is C an element of C? Well, if C is an element of C, then C is not an element of C. Because that's what it means to be in C. To be in C means you're not in yourself. If I'm in myself, then I can't, if C is in itself, it can't be in itself.
So is it a paradox?
It is an absolute paradox. So this implies C is not in C. What if C is not in C? Oh, then it's in C. It's the set of all things that are like this. So that implies C is in C. And so this was painful. Let me give you a little more easily accessible way. There's a story, so people have been thinking about this forever. And this actually,
Who thinks of that?
yeah, right?
What? Did he cut his ear off too?
This created the modern computer. The trouble that this caused is the reason we have computers, the reason you have your laptop. So let me talk about why. Here's like a more accessible way. There is a town, there is a barber in a strange town. We'll just say town. who shaves everyone that doesn't shave themselves. So if I don't shave myself, I go to this barber. I clearly don't shave myself, right? Or like do much of anything to myself. But here's the question, who does the barber go to for a shave?
Oh god.
Do you see what I'm getting at? So if the barber goes, the barber would only go to the barber for the shave if the barber didn't shave himself.
So he shaves himself.
But if he shaves himself, then he can't go to himself to get shaved because he only shaves people who don't shave themselves.
And the barber shaved the barber.
And the barber shaved the barber. Yes, that's nice. So we just wrote an English sentence that hurts. That really, in some ways, so this comes down to, does everything we write have meaning? If I can just write something that seems like a reasonable sentence, does it actually have meaning? So this gets super deep. What does it mean to me? Does this have meaning?
Screw mathematics. What does it mean to me?
Is that sentence true?
Yes.
If it's true, then it's false. If it's, oh, then it must be false. If this sentence is false,
It would be true.
then it would have to be true. So this all comes down to self-reference. So self-referential things. Anytime something is self-referencing, it has a chance to blow up logically and meaning-wise. This is a set that kind of refers to itself in some ways. So self-reference ended up being a huge problem. And so Bertrand Russell, he was a great humanitarian, went to prison for protesting World War I, and just amazing person, like huge activist for social justice, also for logic and philosophy. So Russell and this other dude, Whitehead, spent 10 years. They found this and they're like, wait, something's wrong with math. If I can write this and it's so fucked up, maybe what we're doing at the beginning is wrong. So they set out to rebuild mathematics from the ground up. And they developed this whole thing called the theory of types. And they were hoping that this would put math on solid footing. And they wrote this tome called the Principia Mathematica. And they spent 10 to 12 years on it of their lives. And then they published it. They're like, we've done it. We have put math safe. Made math safe. I'm like speaking like a cave mathematician or something. And then, simultaneously, while this was all going on, there was a dude, Kurt Gödel. And you have to say it's like a German, Gödel, Gödel. It's like an umlaut, so you gotta say it's like weird. A lot of people say Gödel, who was creating his thesis, his PhD thesis. And his PhD thesis was essentially a thing he proved called the Incompleteness Theorem. And in this theorem, in this thesis, he imagined a machine, some kind of a machine that would produce symbols on a piece of paper. It would randomly type out symbols. And in some sense was like writing statements about logic, like proving things, but it was kind of like random, really. So what he showed in his thesis, and he literally proved this, is that there's no way to create a logical system like math that doesn't have these problems. He proved there's no way to create a logical structure that
doesn't blow up in some way. No matter how you create it, you'll always be able to write this sentence here. No matter what your logical system is, this is going to happen in there, and you just can't avoid it. And these guys were trying to prove that you could, and they spent 12 years.
So what did it say? Like, how did they get proved wrong?
Yes. It basically just eradicated that decade of work.
How are they wrong, like, in what they wrote? Like, where was their error?
They weren't thinking in a big enough scope. They were still basically kind of thinking in the way that we had always thought, you know, like we do in math, let's build up from these, take some axioms.
Right.
And they just didn't see the bigger picture of this looming black hole orbiting their work. Yeah. And I think Russell pretty much lost his mind after that. But this thing, this machine that Gödel described, this was the basis for the modern computer. Literally, no one had thought about a machine producing symbols on its own and streams of logic. And this went on to become literally the modern computer. Poor Gödel ended up being locked up. He was gay, and back then that was not something you could be openly. And so he was forced into a sanitarium when they found out about it, and he ended up, he either committed suicide or died in there. They were trying to like inject him with hormones and just do all sorts of just terrible, horrible, inhumane things to him to try to keep him from, to try to make him not gay, right? Like the first conversion therapy. And so he died. Like the person who created the modern computer was locked away and left to rot and tortured.
What was the time period for this again?
Around 1920s.
Wow.
Yeah, it's not that long, 100 years ago. We've come pretty far from his little box, but we haven't come pretty far maybe from what happened to Kurt, right? We haven't grown much as a society. We have in some ways, but not everybody's coming along for the ride. So, I've got more stuff to tell you. It feels pretty anticlimactic to tell you this stuff. How about we start work? Does everybody have a laptop with them or not? How about we check out the assignment? First off, let's make sure the assignment is visible. Because I've been known to maybe not. And let's start on it, and then we can talk about things as they come along, and on Monday then we can talk about probably things I should have talked about, but we'll get there.